Quick overview, or just a very quick recap of what we did last time. So what we did last time was we first investigated, well, we reminded ourselves of the proof of the quadratic formula for solving quadratic equations. Okay, it's a nice little, simple enough algebraic derivation going that if you assume a solution exists to a quadratic equation, it must in fact be given by this formula. Okay? So that's our classic, well-known quadratic formula for solving a quadratic equation. We then attempted to apply this to a quadratic congruence. Not a quadratic equation, but something of the form quadratic polynomial congruent to 0 modulo p for some prime. Okay? I'll do my best with the drills there. So this kind of thing. Now, okay, so it's a different kind of thing to a quadratic equation. Now the object x, we should interpret x as being representing a congruence class modulo p. But, you know, it's still obviously strongly related to behavior of a quadratic equation. So we tried to solve this in the same way. And yeah, exactly the same reasoning went through until we got to this kind of step where to replicate the analysis done for the quadratic equation, we have to start talking about square roots in the system, in the multiplicative system modulo p. Okay? And up to now we haven't kind of broached that subject. But it's clear that these things may exist. Okay? B squared minus 4ac for integers a, b, and c. This is a perfectly good other integers. So this can represent a congruence class modulo p. And it might have a square root. There might be another congruence class such that when you square it, you get b squared minus 4ac. But maybe there isn't, okay? Because we know from real numbers that, you know, lots of real numbers, all the positive real numbers have square roots, but all the negative numbers don't, okay? So this brought us to definition 8.1, okay, which is our definition. Now, when we're speaking modulo p, when we're working in modular arithmetic, we don't really use the term square root, and we don't use the square root symbol, just to leave that alone to apply to real numbers. So we use a different terminology, but you know, it's still helpful to think in terms of square roots and so on, and to make connections back to the real number case. So we talk about quadratic residues. So we say that if there exists an x which satisfies this, if there exists an x such that x squared is congruent to n modulo p, then we say that n is a quadratic residue. It's a residue. It's left behind as a remainder after you divide a quadratic thing, a square, by p. So it's a quadratic residue. It is the square of another congruence class. If there does not exist an x for here, then we say it's a quadratic non-residue. Okay? So a quadratic residue has a square root in the system. A quadratic non-residue does not. Now, we initially, before we started getting into the theory of this, okay, last time we looked at a whole bunch of examples. Okay, so I'm not going to redo yesterday's Monday's lecture, but we started looking at examples. We took a number of primes, 5, 11, 13, 17. What we found in each of those cases was that half of the numbers, just by straightforward experimentation, like for modulo 17, we looked at all the congruence classes, so the 16 of them, 1 through 16, we squared them all, and what we found was that these numbers here occurred as quadratic residues. These are the squares, and that left behind these numbers as not being squares. So these numbers on the bottom row do not have square roots, modulo 17, so they're quadratic non-residues. And the ones in the top did. And in all these examples, the split was exactly half and half. So that strongly suggests that, well, that might be true in general. So that's one of the things we're going to set today. Another thing we noticed was that some of these quadratic residues are obviously quadratic residues. We didn't need to investigate it at all. We should have known from the beginning. Namely 1, 4, 9, and 16. Okay? Because those integers are square integers anyway. So we obviously recognize that they're going to be quadratic residues, because 4 is going to be the square of 2, 9 is going to be the square of 3, 16 is going to be the square of 4, no matter what modulus we're talking about. But the other ones, 2, 8, 13, and 15, the reasons why those are quadratic residues modulo 17 and all these other numbers aren't, that's not so obvious. Okay? And when we looked at different primes, so for instance 2, so 2 is a quadratic residue modulo 17, it wasn't modulo 13, it wasn't modulo 11, and it wasn't modulo 5. So why is it sometimes not a residue and sometimes a residue? Similarly with all the other numbers. We also did a bit of experimentation. I think we did this with the p equals 17. We did this with p equals 13 and 17. We looked at the multiplication tables in those groups. And what we noticed was, so here, R stands for residue, N stands for non-residue. We noticed that they had these nice properties, that when you multiplied together two residues, you got another residue. When you multiplied together two non-residues, you again got another residue. But when you mix them, when you multiply the non-residue with the residue, you got a non-residue. Now remember, residues are the things that have square roots. Non-residues are the things that don't. If you think back to the real number case, positive real numbers are the ones that have square roots, the negative numbers are the ones that don't. And in the real numbers, you have this same multiplicative structure. You multiply together two residues, two things that have square roots, i.e. two positive numbers, ordinary real number multiplication, you get another positive. You multiply two negative numbers, things that don't have square roots, you get a positive number, something that does. When you mix them, when you multiply a negative number with a positive number, you get a negative number. Okay? So we see that exact same structure being present here in the modular case. So our task for today is to try and prove these two observations. So prove that all the time, modulo p, exactly half of the elements are going to be quadratic residues and half of them won't be. And then to try and prove this multiplication structure as well. Okay. So we'll spend a bit of time investigating those proofs, and also maybe finish by introducing some of the notation that we're going to use in the rest of the chapter. So that's a quick review of what happened last time, and a reminder of the definition. But any questions at the moment before we continue? Anything that you'd like clarified on that? So the concept is simple enough, whether or not a congruence class has a square root, whether or not there's something that when you square it, you get back to this congruence class. Then it's called a residue, and then it's called log. The kind of mystery, or the kind of suspicion that there might be something going on that needs to be understood is the reason, how can you tell which numbers are going to be residues, apart from the obvious ones, which are already squares? How is it that some numbers are residues and some numbers aren't? And is there any way to understand what's going on there? And if you're given a large prime and a candidate congruence class, is there any sensible way of finding out whether that's a residue, apart from just kind of the naive method of just squaring everything, squaring all the congruence classes, and seeing if you ever hit that candidate congruence class? Is there any more kind of clever or more sophisticated reasoning we can use to test whether a number is going to be a quadratic residue? Because having that ability is what is going to be what lies behind being able to say whether or not quadratic congruences have solutions. Because whether or not this thing has a solution relies on whether or not this attempt to talk about the square root of this congruence class, whether that's valid, whether you're actually talking about something that exists here. That's going to be that's the place where the existence or non-existence of the solutions here happens. If you okay, so let's so these are these two questions that were left behind from our investigations last time. Okay, so we're going to spend we're going to tackle the proofs of these now. Okay, so this is theorem 8.1. So the proof of it is in the notes, but rather than just read through it, I think we'll just talk through the main points of it here. So we let P be a prime greater than 2. So 2, there's not a whole lot going on modulo 2. There's only 2 elements, 0 and 1. There's not a lot of structure you can impose on a 2-element set. So we won't worry about it. So we let P be an odd prime, so prime greater than 2. And so this theorem says so there are P minus 1 non-zero elements in ZP. Okay. The multiplicative group of congruence class is modulo P. There are P minus 1 elements there. Of course, P is a prime, so P is an odd number, but P minus 1 is even. So this theorem says there are P minus 1 over 2 quadratic residues, and hence there must be the same number, P minus 1 over 2 non-residues. Okay, so that's theorem 8.1. Now, how did we discover this in the examples that we looked at? We discovered it in the examples that we looked at because we just started squaring everything. If you look at the elements in ZP, 1, 2, 3, 4, 5, 6, 7, all the way up to P minus 1, whatever that is, we just started squaring all the elements to discover what the quadratic residues were. But we noticed that when we got to the halfway stage, we'd already done all the work, because the numbers that are in the second half, after you pass through P minus 1 over 2, when you get to the next number, which would be P plus 1 over 2, P plus 1 over 2 is the negative of this number. So it has the same square. This is still true in modular arithmetic. If you square x and square minus x, you get the same congruence class of x squared. So you only have to really go halfway up in order to be sure that you've got all of the congruence classes. Okay? So the first observation is note that 1 squared, which is obviously 1, 2 squared, 3 squared, all the way up as far as P minus 1 over 2 squared. These are all the congruence classes. These are all the quadratic residues. Since the numbers we haven't included, P plus 1 over 2, P plus 3 over 2, all the way up as far as the last one, which is P minus 1. These are all the negatives of the numbers we've already squared. Okay, so you don't discover any new quadratic residues by squaring any of these numbers that are in the second half all the numbers modulo p. Just give a quick example. Let's take the case 17 again. So the elements in 17. Let's just go 13. So modulo 13, when p is 13, these are all the congruence classes. So we square 1, 2, 3, 4, 5, and 6 to discover some quadratic residues. But there's no need to square 7, okay? Because 7 is already congruent to minus 6. So when I square 7, I'm going to get exactly what I got when I squared 6 there. Okay? So I'm not. This is already represented here. And 8 is the negative of 5. So when I square 8, 8 squared is the same as minus 5 squared. So that's just the same as 5 squared. So I've already listed the quadratic residue coming from 5, the square of 5, in my first half of the rest. Okay? So all of the quadratic residues will be contained in the squares of the first half of the system. Okay? Everybody get that? Any clarification? Yeah? Because when these ones are all just the negatives of these ones, when you square those ones, all you do is repeat this list here. Now you might think, oh, that's the proof finished. Now there's certainly p minus 1 over 2 things written down on the page. But the question is, are they all distinct? Maybe there's, so I've written down p minus 1 over 2 symbols here for quadratic residues, but maybe some of them are the same. Okay. So this proves that there are at most p minus 1 over 2 quadratic residues. This shows there are at most p minus 1 over 2 residues. We have to prove that, okay, well, what we saw in all the examples was there was exactly p minus 1 over 2. So we just have to prove that none of these two squares can be the same. Okay. We must show they're all unique. You notice I was careful in the way I phrased this. I said that these numbers are all the quadratic residues. I wasn't necessarily insisting that they were all distinct and separate numbers. I left it open that maybe two of them are the same number. So we must show that they are all unique. And we could do this using a little. Remember, it's hard to show a negative thing directly. Very often, if you want to prove a negative thing, prove the absence of something, you should do a proof by contradiction for it. Okay? So we can do that here. So we'll do a proof by contradiction for this. Proof by contradiction. So what we do is you assume two of them are the same. From that, you'll try and get a contradiction. So if two of them are the same, so I'm assuming that two of these squares are the same. I.e., I'm assuming that a squared is equal to b squared, where a and b are both greater than or equal to 1 and less than or equal to p minus 1 over 2. And I'll assume that a is not equal to b. Okay. So suppose it did arise, let's say this square of a was the same as the square of b, somewhere along there. Well, that would imply then that, remember, these are congruence classes we're talking about. So that would imply that a squared minus b squared was congruent to 0 modulo p. Can that happen? Can a squared be congruent to b squared modulo p? Really, I should say, yes. Congruent modulo p. Well, I mean, being congruent to 0 means that p divides the difference a squared minus b squared. Can that happen? P is a prime number. A squared minus b squared is the difference of squares. Is there any obvious way to proceed from here? Something should kick in when you see a difference of squares. What kicks in when you see a difference of squares? Factorize it, yeah. A difference of squares always has a factorization. A plus b by a minus b. If you're doing number theory, if you're doing any mathematics and you see a difference of squares, immediately consider the factorization. Maybe that's useful. There's another thing screaming out at us to be used here. Can anybody hear it screaming out at you? What are we looking at? We're looking at a prime number p dividing a product of two numbers.
P divides each of them.
Nearly. There's one word, each of them?
Linear combination.
No. I mean, if this was any old number here, instead of a prime dividing a product, there's no immediate conclusion you can draw. So a number divides a product, okay. But if it's a prime number dividing a product, it's not that p divides each of them. Sorry? It's not only one. So what's the other option? At least one. P could divide both of them. It can't divide none of them. So it's a prime number. You can't, you know, if this was not a prime number here, this divisibility could arise because some of the factors of P were in here and the rest of them were in there. And when you multiply them all together, you've got all the factors of P, so therefore P divides it. But P is a prime number. It can't be split up. It either has to reside in A plus B or in A minus. It could reside in them both, but doesn't have to. And it might only divide one of them, but doesn't have to. But the correct conclusion is it divides at least one of them. So we want to proceed logically, you know, because what we're trying to show that our assumption here leads to a contradiction. So P divides, so we can conclude that P divides A plus B or P divides A minus B. Could be both, but it must be at least one. So now our one assumption is split into two cases. We're trying to do proof by contradiction, so we want to show that each leads to a contradiction. So, well, can P divide A plus B? Well, what is A plus B? Where did A and B come from? A and B come from the first half of congruence classes. And they're different. Well, no, they come from the first half of congruence classes. So when you add them, I mean, when you take two things from this side and you add them, what's the most you can get? Well, the most you could get is 12 if you took 6 and 6. But it's even worse than that. The numbers have to be different. The most you can get here, 5 plus 6, is 11. But the prime in question here is 13. But there's very few numbers that P divides. P only divides multiples of P. It's a prime number. Well, anything divides multiples of P. But our A plus B, because A plus B come from the first half, A plus B must be less than or equal to p minus 1. But a plus b is less than or equal to p minus 1. Because they're both less than or equal to p minus 1 over 2. And they're not both 0. They're not both 0 because they're different. And, well, 0 isn't even included. So none of them are 0. So i.e., we're saying 0 is strictly less than a plus b is strictly less than p. So can p divide such a number? No. Okay. There isn't any multiple of p strictly between 0 and p, because p is the very first multiple of p that there is. Okay. So p cannot divide the sum, certainly. So this is a contradiction. You can't have p dividing a plus b, because a plus b has to strictly lie between 0 and p. What about the other option? Could that happen? P divides a minus b? Well, you're getting something similar. What's the biggest difference you can achieve if you take a difference of two numbers here from the left-hand side? The biggest difference you could achieve is 6 minus 1 is 5. No way that 13 is going to divide 5. Maybe you could get a difference of 0. Then 13 would divide 0. Remember, everything divides 0. But you can't get a difference of 0 because we're assuming that a is not the same as b. So we're taking two different numbers from this first half and taking the difference. So there has to be a non-zero difference between them, distance between them, if you like. But the biggest distance is still only half of the prime number, half of 1 less than the prime number. So we can say that, negative p minus 1 over 2 is certainly less than the difference a minus b, and that's less than p minus 1 over 2. And a is not equal to b. These all come from these assumptions about a. So again, p cannot divide that difference. The only way it could divide the difference, well, if a minus b is between these two, the only multiple of p that's in here is 0. But a minus b cannot be 0 because we're assuming that a is not the same as b. So again, a contradiction. So that's good. Both possibilities, both cases have ended in a contradiction. Yeah, question.
Doesn't that only strictly apply if A is greater than B?
So, well, no, I thought I was taking that into account. So I've gone from minus. I thought I was being agnostic here about which is the bigger one. So if you take any two elements from here, the biggest difference you can get, or the possible differences you can get with two elements from here is from minus 5 to plus 5, depending on how you order the bigger one and the smaller one. Biggest difference you can get is 6 minus 1. Smallest difference you can get is 1 minus 6. Is that okay? Can you see that? So the p, remember this example, the p would be 13. So p minus 1 over 2 is 6. And the biggest difference you can achieve, you see, is 5 when you take two different numbers. Yeah. The point is, so what we're trying to contradict, what we're trying to eliminate is this possibility of p dividing this number. So there's only one multiple of p in this interval, that's 0, but we have an additional condition that a is not equal to b. So the difference counts as 0. So where did these cases come from? These cases came from the assumption that, well, the assumption that two of these squares we've listed were in fact the same. So you can't have two of these squares being the same, so they must all be distinct. We've already argued that all of the quadratic residues are contained here. Now we've argued that these are all distinct quadratic residues, so there's exactly p minus 1 over 2. Okay, so we got 1, 2, 3 to p minus 1 over 2. So 1 squared, 2 squared, up to p minus 1 over 2 squared are distinct congruence classes modulo p, distinct modulo p, and all of the quadratic residues. So that proves the theorem. Okay, for any prime p bigger than 2, exactly half of the congruence classes are residues, exactly half of them aren't. Okay. So, and the proof fairly, pretty much just generalizes what we did in the examples that we looked at. Examples we looked at, we started squaring things to discover the quadratic residues, and we remarked, well, we only had to go halfway through the list, because the second half of the numbers are all negatives of the first, so it's just going to repeat the list of squares backwards. And then this final kind of maybe technical detail of showing that when you square any of these two numbers, you never can get to the same answer. Modulo p. We probably could have argued about, if you think back to the chapter on polynomial congruences 2, we proved a theorem by Lagrange which said that polynomial congruence modulo p, it has at, if its degree is n, it has at most n solutions. So we could have actually used that, actually, thinking about it now, because we're talking about the solution of a quadratic equation, x squared equals n. And if you're talking about one of these numbers here, n being 5 squared, we've already identified two solutions for it, 5 and minus 5. So there can't be any others. Therefore, none of these other numbers could square to 5 squared modulo. So we could have gone, I'll just put that down as a remark, could have appealed to Lagrange's theorem, which was theorem 7.1, to prove uniqueness as well. Perhaps we should have done it since we already had it available as a tool, so we've got it, of course, a bit quicker. But in this quadratic case, proving uniqueness was fairly easy to do, just using the definition of divisibility and just arguing carefully about the size of the actual numbers. Okay, so that was the first thing which was left over from our investigation of examples previous time. So the second result was about what happens when you multiply residues, multiply non-residues, or multiply a residue and a non-residue. Okay, has everybody got that sheet? Yeah. So next, multiplying residues, non-residues. So we'll just say we're working modulo p. P is greater than 2. So maybe we can save ourselves from writing out a congruent to b modulo p all the time. We'll just write equations down, but they should all be understood as not really equations, but congruence classes modulo p. So there's 3 results to prove here. 3 results were residue times residue equals residue, non-residue times non-residue equals residue, and non-residue times residue equals non-residue. you should just be able to jump in, prove these. So we'll let U and V be residues. Now this is a classic case of, proof by bridging the gap. Assume U is a residue, V is a residue. We want to conclude that U times V is a residue. Okay? Big yawning gap in front of you. How do you bridge it? Well, you just start. You've got two options. You can either push this down, arguing from your assumption, or you can step back. You can say, well, what intermediate results do we need to get to reach that conclusion? I mean, how can you show that something is a residue? To show that something is a residue, you have to offer up, well, one way to do it is to offer up its square root, show that its square root exists. So if we could say that U times V is equal to the square of something, then we could conclude that it was a residue. We could show that it has a square root. This immediately offers you hope because it gives you a gap. And if you can construct something that goes in this gap, you're home and dry. So where is the thing that fills this gap going to come from? It can only come from the assumptions that you've made. So what does it mean to assume that U and V are residues? It means that U is the square of something, V is the square of something. So there exists what we call these things, an alpha and beta elements of ZP, such that U is equal to alpha squared. So remember, everything that is really congruence is modulo P. It's just simpler to work like this. And V is equal to beta squared. So what goes in the gap? If U is the square of alpha, V is the square of beta, U times V is the square of alpha times beta. Yeah. Disarmingly simple almost. So I left too much of a gap. So if you multiply two residues, you get another residue. Residue is something that has a square root. So if you multiply two of them, the square root of the product is just the product of the square roots. So that's just that basic principle in real numbers. The square root of a product is the product of the square roots. These two, okay, so that was, I think, the easier of the three. Very direct, very constructive. Just make the assumptions, unravel at once. That gives you new objects which construct the thing you need to make the conclusion. These ones are slightly harder because assuming that if you want to prove this one directly, that a non-residue times a non-residue is a residue, well, so you start off by assuming U and V are non-residues. You want to prove that U times V is a residue. But the assumption that U is a non-residue and V is a non-residue, you can't unravel that to give you these other objects which you can use to construct that U times V is a residue. That's a bit tricky because being a non-residue is a negative kind of quantity. It says that nothing exists, so it doesn't give you any tools to work with. Assuming U and V were residues here gave us the tools alpha and beta to work with. So this one, when you start off by assuming U is a non-residue and V is a non-residue, you don't have any. You have the absence of something to work with. That's trickier because you know to get your hands on. Whereas maybe this one would be slightly better to work with, because at least one of our pair, our u times a v, well, at least the v we know is the square of something. That might help us get to here. So now assume u is a non-residue and v a residue, i.e. there exists a, let's call it beta again, such that v is equal to beta squared. Okay, so v is equal to beta squared, but there's no alpha for which u is equal to alpha squared, because u is a non-residue. From this, we want to prove that u times v is a non-residue. Now this doesn't fall out so easily as the first one, okay? Because trying to prove that something is a non-residue, you're trying to prove the absence of something. Trying to prove there is no number such that when you square it, you get u times v. So if the method of direct proof, direct constructive proof, doesn't seem to be available or doesn't seem likely to work, we start to think of other proof techniques. Another common one which we've already used today is proof by contradiction. Okay. So let's try that. So direct constructive proof seems to not be available as it was in the previous one, which is really just saying the square root of a product is the product of the square roots. But it doesn't seem so here. So we'll try proof by contradiction. So in proof by contradiction, you assume the result you're trying to prove is false. So if u times v is not a non-residue, i.e. we assume u times v is a residue. This is an assumption now. Hopefully we're going to show that it's nonsensical to make this assumption. It's contradictory to make this assumption. Well, if you've assumed that it's a residue, automatically, what should your next step be? Well, if you've assumed it's a residue, really you're assuming the existence of something else. It's square root. When you square root, you get it. So we should introduce that. I.e., there exists a gamma in ZP such that u times v is gamma squared. Now what we're trying to prove here, we're trying to prove uv is a non-residue. So we're trying to prove this assumption can't be done. So we're going to try, we have to get a contradict, somehow this gamma should not exist. How do you show that that gamma does not exist? You have assumed it exists. But what we need to do is show that assuming it exists leads to a contradiction. It leads to something that contradicts something that's already in force. Can anybody see? Can anyone see it or see what it might be? What's the contradiction? I mean, it's got to contradict something that's already declared on the page or assumed on the page as a fact. We've assumed V is a residue. Fair enough. There exists a beta with that property. But we've assumed U is a non-residue. How is that assumption looking in the face of what's on the board at the moment? And also just some straight substitute, some straight kind of algebra. So we've assumed here that v is equal to beta squared. U is not equal to anything squared. And we've additionally assumed, for the purposes of contradiction, that u times v is equal to gamma squared. You're searching for a contradiction, so you try and push all these assumptions together. Well, how should you do that? You should substitute. What does that seem to be saying? We've already assumed that u is not equal to the square of anything. I shouldn't really write the formula like that. You get the idea. There does not exist anything you can put there to make u be the square of that. But what does this seem to be saying? Can I make u be a square of something here?
Alpha over beta.
Gamma. Slightly better language than alpha over beta. Remember, these aren't real numbers. These are congruence classes, modulo p. Yeah. Talk about the inverse of beta rather than saying over beta. But correct intuition. So gamma times beta inverse. Okay, you multiply both sides by the square of beta inverse. Clears the beta squared from there and gives you 2 kind of like a square, really you've got gamma, gamma, beta inverse, so you got the square of gamma, beta inverse. Does beta inverse exist? That's another question you should be slightly cautious about. Does beta inverse exist? Well, where does beta come from? Beta is an object in this group of multiplicative congruence classes. So beta has an inverse. Everything that's in here in the multiplicative group of congruence classes, it has an inverse. So there is an inverse to beta. So hang on a minute. This is saying u is a residue. But we started off the argument saying u is not a residue. It can't be both. It can't both be a non-residue and a residue. So there's some problem. Where did the problem arise? So you roll it back and you look at the last assumption you made. The last assumption we made was that this gamma existed. We assumed that u times v was a residue. We assumed it for the purposes of contradiction. And if you do assume it's a residue, immediately you get a statement which contradicts an earlier assumption. So it means that that assumption cannot be done. Can't assume that u times v is a residue in the presence of something where we've already assumed u is a non-residue. So that gives us our result that a non-residue times a residue equals a non-residue, because it can't equal a residue. The only other option is a non-residue. So this would imply that u was equal to gamma beta inverse squared, which contradicts the fact it contradicts the assumption here that u is a non-residue. So we cannot assume that u times v is a residue, therefore the only other option is it's a non-residue. So that proves that n times r equals, and n times an r is an n. So there's one last case for you to prove. So I'll leave this with you. So remains to prove that if u and v are non-residues, then U times V is a residue. Now this is slightly harder still, because both assumptions are kind of negative. So you don't get anything to go on from assuming U and V, you get the absence of something. You're trying to prove something kind of positive, trying to prove a square root exists. So a kind of hint here is need a counting type argument for this. Counting type argument for this using theorem 8.1. So I'll just leave that with you for the moment. I'll prove this at the start of Monday's lecture, just to set that. But you can try it yourselves in the meantime. Oh no, sorry, we can do it at the tutorials next week. We'll try and go about constructing the proof of this, but you'll need some kind of counting argument using the results we've already proved and theorem 8.1. Okay, we better finish there for this morning. I'll see you all later.